Ready? Hello, everyone. On behalf of the entire Gator PhD team, I'd like to welcome you all to our presentation on our Phobos and Deimos sampling mission, the geological acquisition to observe regolith from Phobos and Deimos, or Gator PhD for short. Before we begin, I'd like to inform everyone that we do have extra slides at the end of the presentation that we will not be presenting, but we will have them for questions at the end. So now let's quickly introduce the members of our team.
Hi, I'm Victoria Allen.
Hi, I'm Alec Gray.
Hi, I'm On Huck.
Matthew, you're on mute.
Sorry, I'm Matthew Madelon.
Hi, I'm Patrick Moorhead.
Greetings, I'm Bryce Moran.
Hello, I'm James DePadua.
Hello, I'm Macaulay Redding.
Hi, I'm Tiffany Young.
So first, we're going to go over the mission we're designing around. We must design an exploration excursion vehicle, or EEV, to explore the Martian moons, Phobos and Deimos. It must support 2 crew members throughout the entirety of the mission who will stay inside the EEV. It must conduct scientific exploration of the moons, and the total mission time itself cannot exceed 30 days. It must also support sample retrieval from both destinations with a minimum retrieved mass of 50 kilograms from each. The EEV itself begins a 5-sol orbit awaiting the DST. The mission itself begins on January 1st, 2040. And lastly, we are shooting for a budget of $1 billion, launch cost included. So going over the CONOPS, the EEV itself is assembled and launched, initiating a Hohmann transfer from Earth to Mars. When it arrives to Mars, we're using aerobraking to slow down and terminate the Hohmann transfer before initiating a prograde burn to enter a circular parking orbit awaiting the DST. Once the mission begins, we initiate a bielliptic transfer down to Deimos. When we arrive at Deimos, we enter a quasi-orbit with Deimos, terminating that bielliptic transfer. Sample collection begins, and when that concludes, we initiate a bielliptic transfer, leaving Deimos and initiating a quasi-orbit with Phobos. Once we arrive, sampling continues at Phobos, and then when that finishes, we leave the Phobos quasi-orbit, enter a bielliptic transfer to return back to the DST parking orbit. And when we arrive, that concludes our mission.
The first phase of our mission is the interplanetary transit. To perform this transit, we needed to select a launch vehicle, and we performed a work study using NASA's Launch Vehicle Performance tool, where we compared a few criteria, but primarily the characteristic energy of 3 spacecraft that we deemed viable for comparison. Those were the Atlas V, the Vulcan in its VC6 configuration, and the Falcon Heavy in its fully expendable configuration. On the right side, you can see a graph produced by NASA's performance tool, where each of the spacecraft's capabilities are represented by the colored curves, and our target characteristic energy is represented by the black vertical line. If you take a look at that, you'll see that the Falcon Heavy far and away outperforms its competition. This, combined with the fact that it is the cheapest of the 3 to launch, led us to decide on the Falcon Heavy being our launch vehicle. Additionally, we have chosen the Falcon Heavy over upcoming spacecraft such as the NASA SLS and SpaceX's Starship, because the Falcon Heavy is already flight tested and flight proven, while these upcoming craft are still in their experimental and prototype phases. With our launch vehicle selected, we were able to design our interplanetary trajectory. We chose a Hohmann type transfer for maximum efficiency to minimize our delta V requirements, both for departure and arrival. Using a tool developed by the Polytechnic University of Madrid, we were able to determine our optimal launch date to be July 2nd, 2035, and our optimal flight time to be 204 days.
So as Matthew mentioned earlier in the mission requirements, we need to visit both Phobos and Deimos within 30 days and to perform 2 days at each moon for sample collection and science. This led to a trajectory design goal of having the lowest time and lowest delta V, and ideally having a good combination of both of those. Initially, we started with a trade study to examine the mission sequence. So we looked at going from moon to moon, or going from moon back to the DST, and then back to moon, and then back to the DST. And we decided to go to Deimos and then Phobos based on the inclination field burning costs. After this, we performed an exhaustive search that examined some 2,000 different starting orbits around Mars at varied eccentricity and inclination. That exhaustive search ended with these numbers you see here in the table on the right. The text on the left here is basically a summarization of the CONOPS. But the EV departs and spends 204 days in transit to Mars. Upon reaching Mars, it enters the orbit of inclination 1.15 degrees with a period of 5 solar days. When the EV leaves from the DST to Deimos, it will spend 63.55 hours in transit. It will spend 2 days collecting science. And then when it departs from Deimos to Phobos, it will spend 9.16 hours in transit. And when it departs from Phobos back to DST, it will spend 75.56 hours in transit. The total mission time is 13.4 days.
We'll now transition into the system design overview for the Exploration Excursion Vehicle. We're going to start with the docking system. After thorough consideration, we decided to go with the IDSS, or the NASA Docking System, NDS. And this is due to its capture success rate, its low power safeguards, and it's universally accepted. More specifically on the EEV, it'd be the NDS B1, which is seen in the figures on the right. Structural attachment is done through soft capture in the top right, and then mating for pressurization and power transfer through hard capture in the bottom right. For thermal and pressurization properties, there is a successful mating range between -38 Fahrenheit and 122 Fahrenheit. And if the temperature is outside this range, we've determined conduction of heat from the life support system will be enough to keep it in this range. And now we'll go to the next slide.
Now, to determine the best possible landing sites for our mission, we conducted a work study based on surface roughness, the surface material variety, solar coverage, and the amount of delta V required to reach each site. And from this study, we were able to select 2 landing sites for each moon. For Phobos, we selected Stickney Crater, which you can see on the top left, as well as the Phobos Grunt landing sites, which you can see on the top right. For Deimos, we selected the South Pole, which you can see on the bottom left, and its North Pole, which you can see on the bottom right. And now for our mission, the EEV does not actually land on Phobos or Deimos. Instead, it achieves a quasi-orbit next to each destination body. And for this, the EEV has the ability to perform station keeping in its quasi-orbit and maneuver between landing sites and maintain a predetermined altitude above each site. For Phobos, it is positioned above the landing sites on Phobos at an altitude of approximately 20 kilometers, while for Deimos, it maintains a altitude of 3 kilometers above the surface. And for all these tasks, our vehicle will use its reaction control systems and its primary propulsion unit.
Now, our sample retrieval design is primarily based on NASA Jet Propulsion Lab and Johnson Space Center work studies. Our original design relies on the regolith collecting CHOMP surface exploration vehicle that makes use of an extending arm clamshell mechanism known as the Trident. Now, the CHOMP surface exploration vehicle is a touch-and-go sampling vehicle made of AA 2050 aluminum and is powered by solar arrays and ion batteries. The CHOMP vehicle utilizes 8 Dawn Aerospace bipropellant B-20 RCS thrusters to maneuver itself in the microgravity environment and hover itself over the surface of the moons for material collection. Now, the CHOMP vehicle carries the Trident sampling system, which handles the majority of the regolith extraction, and CHOMP is also stored in a pressurized module within the EEV during transit and is released once the Parkey orbits are required.
Sampling is conducted by our Trident sampling system. This is an in-house design we came up with based on some work studies done by Jet Propulsion Lab that they conducted in the neutral buoyancy lab. Essentially, they came up with this idea that the only effective way to collect loose samples such as regolith in a microgravity environment is with a clamshell tong device. So we've developed a fully automated one with interchangeable heads so that our samples do not have any sort of cross-contamination. And additionally, to ensure mission completion, we have built-in redundancy with a second motor on the end of it to perform the opening and closing in case one of them fails.
Here are our science objectives. There's 5 of them, and we base them off of our mission requirements and other missions with similar objective goals. The first 2 objectives involve the sample retrieval and equipment specifications needed to analyze the Martian moons. Objectives 3 and 4 include measurable quantities that will be used to analyze those moons, such as local and global characterization, in situ observations, and research. And lastly, objective 5 is our main mission goal, which is to determine the formation of the moons. And this gives scientists insight on how the inner solar system was like before life on Earth, and it helps turns us to discover the inner workings of other solar systems for possible life elsewhere.
In order to select scientific equipment that accomplishes our scientific objectives, we have the following selection criteria. The first one is surface contact with samples, since our samples have to be isolated the whole time. Weight and size, since we have a 200 kilogram limit for scientific equipment. Usage, because of redundancy, whether or not the equipment can be used on Earth or only within the spacecraft. Surface mobility versus EEV depends on the location of mounting for the scientific equipment, and then surface contact with the moons for contamination in the moon's environments. From this, we found that for the goal of local global characterization of the Martian moons, we could select the wide angle camera, narrow angle camera, and stereo camera. For the objective of in situ observations of material on Martian moons, we selected the Mossbauer spectrometer and long wave planetary radar. And then for solar winds and magnetic fields research, we selected the neutral gas and iron mass spectrometer, Langmuir probe, solar wind electron analyzer, and 2 solar energetic particle telescopes, as well as superthermal.
Next, we will talk about the crew accommodations and life support systems. For the atmosphere, there are 4 major components that make up our EUV. The first is the air revitalization system. A trade study was conducted to determine the best choice for this, and it was found that in terms of both mass efficiency and CO2 removal rates, the TAS, or thermal amine scrubber, would be our best choice. This was designed by NASA JSC, sorry about that. And it is designed to fit within a ISS standard express rack along with our oxygen generation assembly. This also acts as our humidifier, or humidity control system, sorry. The oxygen generation assembly from the ISS was determined to not be feasible for a mission such as this, according to a report published by NASA. However, the same system can be modified for our needs. The removal of the nitrogen purge equipment, downsizing of the power supply system, and removal of the wastewater interface was found to give it optimum reliability and reduce the mass enough for our mission. The temperature control system is made up of a series of heat exchangers and heat pumps mounted along the ventilation system. These are going to be used to regulate and control the atmospheric temperature within the EUV. Finally, for fire detection and suppression, a series of sensors are mounted along the air ducts. These sensors being used are extremely silent and require little to no power, or fairly negligible amounts of power rather. And in the event of a fire, sections can be sealed off to deal with it.
For our crew's potable water supply, we are going to be recycling any recoverable wastewater, utilizing the Universal Waste Management System from NASA, as well as a multi-filtration system to step it up to full potability. In the event of any emergencies with the potable water storage tanks, we will also be bringing along additional contingency water bags for emergency storage.
Now, since this is a crewed mission to provide the necessary nutrition for the astronauts on board, our design uses the ISS Advanced Food Hardware System. The crew will be required to consume at least 3,000 calories per day, which is roughly 8.7 kilograms of solid food per astronaut for the 14-day mission period, which the AFHS is more than capable of handling. Now, in case of a medical emergency, the crew compartment will also be equipped with the ISS crew healthcare system. The CHECS carries all sorts of medical equipment for a variety of emergencies, carries a defibrillator, a variety of pills, and it even tracks the astronauts' vitals throughout the duration of the mission.
Due to our time constraint, I'm just briefly going to cover waste management. We've decided to break it up into both recoverable and non-recoverable waste. And we did a trade study for 2 astronauts to see the daily waste produced. So we got both a mass and volume out of that. And from that data, we determined that the recoverable waste will be recycled through the UWMS, as mentioned by Patrick, as well as the system's filtration system, and the metabolic solid waste. So the non-recoverable waste will be just stored in containers. And now we're going to discuss the EEV flight systems, starting with propulsion.
So the propulsion technology, we examined 4 different technologies: chemical rockets, electrothermal, electrostatic, and nuclear. And chemical was the overall winner. And this led us into our engine trade study. We did not examine specific fuel types. Instead, we just bundled them with the specific motor because we did not want to develop a one-off motor for this mission. You can see the trade study for the motors below. And above all, we put the useful load as our highest individual requirement, just due to our tight mass margins.
Based on the trade study that Bryce discussed, we were looking for a fuel with a low propellant volume and a very high useful load. Cryogenic propellant was selected just due to its high performance and it being able to reach the delta V required. We did consider space storable fuels, but we ran into an issue with storing the propellant and propellant mass. So the engine we decided to go with was the RL10C3 or the RL10CX, which is more in the development stage, but is a future 3D printed version. But it has an ISP of 460.3, 6,600 kilograms of bipropellant fuel, and a fuel to oxidize ratio of 5.7 to 1.
Lastly, for the propellant system or propulsion system, we have the propellant tanks and feed. The tanks are to be cryogenic safe composites based on research from NASA's X-33 program. And so the tank is composed of an inner carbon fiber pressure vessel and then a outer polyurethane foam for insulation. For example, on the hydrogen fuel tank, this foam is about 3 inches thick. Tank sizes were based on MATLAB code using densities and ideal gas law, and propellant feeding is performed by engine-driven turbo pumps that come with the RL10 motor.
For EEV flight guidance, our design relies on the Autonomous Optical Navigation System, or AutoNav for short, which was designed by NASA JPL for deep space missions. As illustrated in the graph, AutoNav autonomously computes the vehicle's position and trajectory through a process called triangulation, where the computer references asteroids, planets, and other satellites against a set of background stars.
AutoNav relies on a variety of sensors, the details of which we are not going to get into just at the moment for the sake of time. But if you have questions about any of these specific sensors, please feel free to ask them when we finish the main portion of our presentation.
Now, to physically alter the EV's flight trajectory and position, several Dawn Aerospace B-20 RCS thrusters will also be used for the EV as they are used for the CHOMP SMS design. The thrusters are fueled by nitrous oxide and propylene with no cryogenic requirements and will be used for quick, short maneuvers.
For slower, more controlled maneuvers, we're going to be using the reaction movement wheels. These will help us to maintain a body fixed orientation around around Phobos and Deimos. And additionally, these can work in unison with our RCS thrusters to perform angular momentum desaturation.
Now for our electrical system. This table shows the different subsystems that will be implemented into the EEV and their total power consumption. So most of the power will be going towards atmospheric, communication, and food maintenance. The baseline power, or the power that the EEV continuously needs to operate, is 15 kilowatts, which includes a 33% efficiency drop, meaning that 1/3 of the power is lost to the system. And the peak power consumption is 41 kilowatts, and that includes the total power needed to recharge the batteries for dark times. So solar power was chosen as our primary power source. The ATK Megaflex was chosen to be our solar array design based on its low weight, compact storage, and high power production. The design is an umbrella-like structure when fully deployed and folds up like a handheld fan for storage. 2 array blankets were chosen instead of 1 in order to balance the center of gravity. And each blanket has a diameter of 12.22 meters, totaling for a surface area of 234.9 meters squared. Lithium-ion batteries are our secondary power source. The SAFT lithium-ion battery pack was picked based on its high power to weight ratio. 6 batteries with a C rating of 0.5 will power the EV during the dark times, meaning it'll take 2 hours to fully charge and discharge each battery, and the total mass of our power system is about 1,100 kilograms. Because this is a crewed mission, a fully regulated direct energy transfer system will be implemented. The solar arrays will power the power bus directly without any intermediate components, and then the bus will then supply the power to each individual component. The FRDET prototype board, as shown at the bottom, has different components that, like the bidirectional converter, which acts as a voltage regulator, a control unit, which is in charge of dissipating the power from the converter, and also the voltage and current sensors that will control the power to the subsystems. And the power system components are located in the unpressurized cabin. A 10 AWG wire will run through the spars of the solar blanket and connect the solar panels to the power distribution. And based on the total amps of each individual subsystem, a 16 AWG wire will connect the bus to each individual electronic payload. And short circuits and current limiting resistors will be implemented to each component to protect them from damaging another.
I will now be talking about the thermal management systems. In order to design our thermal management systems, we first have to define the requirements. In terms of thermal load requirements, our total external thermal load was calculated to be 15 kilowatts, and our total internal thermal load was found to be 41 kilowatts. Additionally, there are temperature restrictions that we need to take note of. As you can see in the table, a lot of these temperature ranges fall within the same temperature ranges as people, meaning that a lot of our equipment can be safely stored in our pressurized section. However, you can see that our liquid hydrogen must be kept below -253 degrees Celsius, and our liquid oxygen has to be kept below 163 degrees Celsius. Because of this, we have to have a thermal system specifically for our propulsions. This means that our fuel tanks will be covered in polyurethane foam and will each have their own carrier coolers. Around this unit will be spacecraft skin, and around the spacecraft skin will be a layer of MLI specifically for the propulsion section. In terms of carrier cooler, we'll be using Ball Aerospace's 10 Kelvin carrier cooler that's currently in development. They're well known for using their 80 Kelvin carrier coolers in space applications. So even though this carrier cooler is still in development, I feel that they will be finished by the time our mission needs to start. Another thermal requirement that we had to take note of is solar arrays, because their max operating temperature is 150 degrees Celsius. We found that the solar energy they'll be collecting is about 119 watts per meter squared. This means the temperature that they're going to be experiencing is about 137 degrees Celsius. This is about a leeway room of about 12 degrees Celsius. So for this, we're going to apply a thermal coating of white paint to the back of the solar arrays for worst case situation thermal loads. Here you can see the components used in our thermal management systems. This includes radiators, heaters, pumped fluid loops, MLIs, louvers, cryogenic coolers, and radiative thermal coating. The total mass of this will be about 2,080 kilograms. The total volume will be about 39 meters cubed, and the total power will be about 1,700 watts. This is a list of materials and thermal coatings that will be used relevant to our thermal management systems. In terms of thermal coating, we have to note the external surfaces, electronics, radiators, antennas, solar panels, and louvers. In terms of material, thermal-wise, we need to be concerned with the materials of the radiators, heaters, pumped fluid loops, louvers, MLIs, and foams. For cryo coolers, the material that will be used will be the manufacturer's material because it is an off-the-shelf product compared to the other custom-made products. This here is our systems diagram for our thermal management systems. As you can see, there are 4 loops in this image. However, there are 8 redundancy loops in total for our system. There are only 4 shown because these 4 are repetitive for the other 4. There are 2 types of loops. The first one is for equipment along the walls, and the other one is for equipment placed in the center, but they're just about the same. The way these loops work is that first it starts with the heater that heats up our internal surfaces, and then there are pumped fluid loops attached to our equipment that will be taking the heat from the heaters as well as thermal waste from our equipment and take it over to the louvers and radiators, which will regulate and expel any excess thermal waste, thus creating external heat loads.
Next, we have our communication system. So radio frequency was chosen over laser communication because it requires less accuracy. It's been tested and lasers are strongly affected by the atmosphere. Each component's total mass and power requirement is displayed in the table, and a functional schematic that demonstrates the flow of communication is shown on the right. So the command and data handling system is basically the brains of the EUV and contains a flight computer, which is used to calculate and record all necessary flight information. The ultra-stable oscillator is designed to stabilize the frequency of the radio transmitters, and this is most commonly used when the EUV passes behind objects in space, which obstructs the communication with the ground. And lastly, the bandpass filter is used in order to prevent the transmitter from interfering with any stations by only allowing certain band frequencies to pass. On the EEV, there will be 2 small deep space transponders, one that will be used for backup in case of emergencies. The transponder plays the role of both transmitter and receiver, and its main function is to convert electrical signals to radio waves to send to Earth and vice versa to get the information from the ground back to the EEV. 3 amplifiers will be on board, 1 35-watt Ka band and 2 100-watt X band traveling wave tube amplifiers, and their function is to boost the radio signals enough for the deep space network to detect them. And then lastly are the antennas. There will be 1 high gain antenna with a 3-meter dish and 2 low gain antennas positioned on the back side of the high gain antenna. The high gain antenna is the primary source of communication and requires high accuracy, while the low gain antenna provides low rate communication in case of emergencies and focuses its beam more broadly.
Next, we will talk about the spacecraft layout and structure. In terms of the configuration and specifications, the EEV had to be designed to fit within the Falcon Heavy long configuration fairings shown on the right. To do this, a maximum radius of 4.57 was chosen. This is along the command module and chomp module. The command module is pressurized and houses the crew, while the chomp module houses the SMS. This module can be depressurized in order to release the SMS. The propulsion module houses all equipment that does not need to be stored in a pressurized environment. Next, we have some images of the EEV with the solar panels unfurled and a basic image of how the SMS would be mounted within the chomp module.
Moving on to the structural analysis, the structure itself is treated as a monocoque cylinder. We then analyzed the pressurized modules in space, which were modeled using hoop stress. We then also analyzed the launch conditions using the max compressive bending stress, which combines the combined analysis of the longitudinal stress, the bending moments, and the pressure differential experienced during launch. Also on the right, you can see the loads applied to our spacecraft during launch on the Falcon Heavy, pulled from the Falcon Heavy user guide. Lastly, we completed one final check of the compressive proportional limit of the selected materials. The analysis calculates the structure thickness and the resulting structure mass. This analysis also presumes welding manufacturing, and the factors of safety we used where 2 for ultimate tensile stresses and 1.5 for compressive yield stresses. Moving on to the material selection itself, using the previously mentioned analysis, we developed a MATLAB code to run through the various loads imparted during launch and the pressurizations in space and the different material selections and their specs seen on the right. The resultants for structural thickness and resultant structural weight, which were calculated, were then compared against each other, and the lightest resultant structure was selected. The material of that was 7075 T73 aluminum with a thickness of 2.1777 millimeters. Lastly, we have our cost estimation. We use the Johnson Space Center developed Advanced Missions Cost Model, or AMCM, which is a multivariate parametric cost estimation model taking into account 260 past programs. The actual equation and constants can be seen on the right. The actual inputs that we have are Q for quantity, which is 1, the mass itself in pounds, which is just over 26,000 pounds, the specification of the mission, which is the type of mission. We use 2.39 for planetary, the initial operational capability, which is when the mission year begins, which is 2035, the block, which is 1, which is we have a clean sheet design, so there's no successive design component, and the difficulty we have is 0.25. This is going from a negative to positive scale, with 0 being average. Negative is slightly easy, so we put ours as slightly easier than average, as we don't do anything that is technologically extremely difficult. And we also tried to reuse as many components or reasonable components as possible. This resultant is then multiplied by 1.66 to convert it to cost in fiscal year 2021. And the total cost for the whole project, from design, development, production, manufacturing, assembly, launch, and operation, comes out to just under $10 billion. Comparing this to previous missions or spacecraft or human crewed spacecraft or missions to Mars, we think this is reasonable, comparing the future launch date, the actual weight of the spacecraft, the operational capability that we're providing. And so although this is over our budget, we think this is actually a reasonable estimate for what we're hoping to accomplish.
So with that, we'd like to thank everyone for being part of our CDR presentation, and we'd like to open this up for questions, comments, and/or happy thoughts. Additionally, as Alec mentioned earlier, to help support any questions you all have, we do have some extra slides.
Okay, thank you for your presentation. Any question from our audience?
I think the first thing we've got to talk about is cost, right? I mean, your customer asked for a proposal for a $1 billion mission, and you came back to them with a proposal for a $10 billion mission. Is your position that they're just, that they're totally unreasonable with expecting a $1 billion mission?
If they're asking for $1 billion for everything from development, design to operational capability, then that is unreasonable. The actual request for proposal asked for the cost of the spacecraft. We weren't entirely sure if that was specifically manufacturing or assembly or any specific part of the actual total cost for the spacecraft. So we thought it was reasonable to include everything just to be safe. And that
cost, that $10 billion cost estimate is coming from the cost estimate formula. What does that represents a full development program, not cost of a mission?
Yes, that's full development program.
Okay. Do you have a sense of what's driving that?
The mass, definitely the mass, which we're sending a lot of mass out to Mars. I would definitely say that if we've been trying to minimize mass as much as we can. It's just been very difficult because there is so much equipment you need to get to Mars. So, and also the fact that we're using a clean sheet design, which is, it's the only option really. There's no other spacecraft that exists that we can further develop upon. And so clean sheet is also driving the cost way up.
Okay. Out of curiosity, how does your mass compare to, say, an Apollo mission?
It's actually, the mass we currently have is lower. We're coming in at just under 12,000 kilograms, which is, or we're just over 12,000 kilograms, which is the max we could get to Mars. But surprising, that's lower than things like Apollo or things like Orion.
Okay.
So,
what can we talk more about the cryogenic propellant? That seems like it adds a huge amount of complexity. I mean, just keeping things cool is its own problem. Storing hydrogen is a significant issue. It seems like there are a lot of negatives there that I would have expected to come out in a trade that, that another system of propellants may have been more beneficial. So where does that show up in the trade?
So if Patrick, would you mind going to that particular slide? The biggest issue really for us was our useful load, because any propellants that weren't cryogenic, like if we weren't getting above ISPs of like 450, we weren't going to have a high enough useful load to do anything with. And that was really our biggest concern, was just the spacecraft eating up all of its mass in terms of propellant. As it is now, with the RO10, we were able to get our mass requirements down to only 6,600 kilograms, which means we get a non-propellant mass of only like 40% of the spacecraft is like non-propellant. Because if you can look at like the RD0125 Alpha, which is a modification of the Russian RD0124, then that's using RP1, and that would only have 4,000 kilograms of useful load. And so that was just our largest driving factor, is making sure we were going to be able to meet our structure, thermal weights, our atmospheric weights, the weight for all the equipment and astronauts, and giving us as high a mass margin as possible. And unfortunately, we ended up having to go with cryogenic fuels to meet that high performance. We really didn't want to, but if we did not do that, we would have to end up getting a new launch vehicle, and so we'd have to be going off of SLS or Starship, both of which are in development. And
they are, but they're in development in 2021, and your mission is launching in what, like 2039, 2040,
2035. Okay. And our issue with that is we couldn't.
15 years of development. Is it a reasonable bet to rely on something of the scale of SLS or Starship that would be capable of launching your system?
We are willing to bet that they will be done within 15 years. But our biggest issue was trying to find documentation for their exact like fairing size and payload.
Mm-hmm. Things like payload and the actual loads applied to the structure during launch basically means we wouldn't be able to really design the structure or figure out an estimate mass, because there really isn't anything we could find.
I think it would be fair to make some engineering judgment assumptions on that sort of thing. I was talking actually offline the other day with I think with Dan Plucky, who's also on the call, about relying on Starship as a launch vehicle when it's still in development. But really, you're relying on a deep space transport that isn't near as close to operation as Starship. So I don't think that's necessarily the roadblock that you guys are seeing. And if it enables a simpler propulsion system, I think it might be worth taking that on as risk. So I'll sort of yield the floor to some other folks if they have comments, but I've got a couple of things more I could ask if we have time.
All right. Also, thank you for coming back to see us, Mr. Singer, and accepting all our LinkedIn requests.
Any question from our other audience?
We don't bite much. Mr. Gills, perhaps anything? You showed up to our rehearsal the other day. So.
All right, so I'll keep going then. So you mentioned, so you're not actually physically landing on a body, and I'm not even sure I know what it means to land on a body that has such low gravity. I think we're like 0.005 and 0.0005 for Deimos. How are you station keeping? Are you in something like, I'll call it a geosynchronous orbit, but I know that's not the right term. Are you in orbit around the moon at some station, or are you constantly expending fuel to maintain a station?
So we're in a quasi orbit with these moons, which means that instead of orbiting the moons, we're actually orbiting Mars, but just in the same orbit profile as the moons themselves.
So are you saying at 3 kilometers from Deimos, you're not within Deimos's sphere of influence?
Yeah, for Deimos, no. Seeing as its gravitational constant is so low, the Martian sphere of influence is going to have far and away a larger effect. But we do have the RCS systems on board with both the thrusters and the movement control wheels. So we do have some padding in our estimated fuel expenditure in the event that we, end up having to use more than we expect to maintain these quasi orbits.
Okay. And do you anticipate, because these are significantly irregular bodies, and if you're not even in orbit around them at all, do you not so much for station keeping, but for like orientation keeping, are you anticipating being next to large irregular bodies to have an impact on like fuel usage for that?
I will be honest with you, we haven't taken the irregularity into account. We did select our quasi-orbit altitudes to minimize just the generalized effects, not accounting for irregularities. But in addition to solar exposure, that's the other reason we're sitting at 20 kilometers above Phobos.
Are you using Phobos as radiation shielding?
No, sorry, that was poorly communicated.
Yeah, you want
right. We want to be in the sun.
Okay,
That's
yeah.
what I'm saying. It's like in addition to wanting to be exposed to the sun, also to minimize its gravitational effects. That's why we're sitting so much further from Phobos than from Deimos.
Okay.
Because it's its gravitational constant is an order of magnitude greater.
Yeah. Okay.
But it is still a milligravity environment.
Yeah, it's certainly not high. And yeah, I guess I hadn't really thought about how close you physically need to be to that small a body to be outside of Mars's sphere of influence. Yeah, man, I'm gonna have to break out an old astrodynamics textbook. Let's see. You had mentioned on your structural analysis that you had a factor of safety that you were planning for of 1.5 on compressive yield and 2.0 for ultimate tensile strength.
Yes.
What's driving those factors of safety?
Honestly, they were from a reference that I was using. It was
that's higher than what I'm used to seeing in space applications.
Yeah, it is definitely higher than what I initially thought. Initially, I was thinking somewhere along the lines of like 1.3. But this book,
that's lower than what I've seen in space applications.
Yes, I know it's, but here's the thing: we're going to be carrying people. We're going to be going to Mars. We figured safer is better than less safe. So,
okay. How much does that drive weight of your structure versus if what I would consider a standard space application factor safety would be 1.5 for ultimate. So how if you're going to 2.0, are you carrying 33% additional weight in your structure, and how does that compare to the overall mass of your vehicle?
To be honest, I haven't run the numbers comparing different factors of safety. I found more so that a driving factor of mass is more so the material selection. And so that I saw was driving our mass more than what the factor of safety was doing. But actually, now that you mentioned that, I'm probably going to go back through my MATLAB code and test some different factors of safety to come in and see how.
Yeah, I'd be interested. I mean, I'm sure NASA has copious white papers about Martian mission type of human missions. And I'd be interested to see what they're assuming for factors of safety. Certainly, I mean, you could look at Apollo, and I think Apollo was 1.4, and that got inherited by the space shuttle program. And since then, I think they've bumped that up to 1.5. But Apollo, I mean, it doesn't have all of the same, challenges in terms of remoteness, but it's got some of the same challenges in terms of remoteness. And if 1.4 was acceptable for Apollo, and I think it was, it might be that 2.0 is a little on the over conservative side for you guys.
Yeah, I think that's fair. The other thing I wanted to do is, because right now our structure is currently using a monocoque design, and I think that's also driving the weight way up much more than it needs to be. So I'm going to go back and start assessing various structural layouts as well to see if we can try and minimize that. So
checking time, I see I'm over time. I got more questions I can write in my notes though.
Well, I mean, if you have any more questions, we're free to answer them. But if you have to go to the next group, I know that is coming up. So it's whatever works best for y'all.
Yeah, we're happy to keep answering questions. So,
And we can share our contact information through email in the chat for future meetings if anyone is interested in that as well.
Sure thing. All right, I'm going to jump over to the next meeting. Good job, guys. Go get it.
Thank you.
Thank you.
Thank you.
Thank you, Go Gators.
thank you.
Thank you.
Hey, good work, everyone.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks for stopping by our dress rehearsal the other day.
Yeah, sorry, I had the wrong Zoom. I was looking for the 1 o'clock yesterday.
Fair.
No,
You're
thanks
all
for
good.
coming. So thanks for coming.
A little confused on that one.
Mhm.
Okay. So it's us now, and so I just